At the end of the 19th century, physics appeared to be a finished masterpiece. The laws of motion described by Newton, the theory of electromagnetism unified by Maxwell, and the thermodynamic principles governing heat and energy together painted a picture of a universe that was orderly, predictable, and continuous. Many physicists believed that all that remained was to refine measurements to a higher precision. Atoms, if they existed at all as physical objects, were assumed to obey the same rules as planets, pendulums, and waves. Matter was thought to be reducible to tiny particles moving smoothly through space, responding deterministically to forces. This confidence, however, was built on assumptions that quietly failed when confronted with the microscopic world. Classical physics was deeply rooted in continuity. Motion was continuous, energy could vary by arbitrarily small amounts, and change was smooth. If an object lost energy, it did so gradually. If it gained energy, it absorbed it continuously. These ideas worked remarkably well for everyday phenomena and even for celestial mechanics. The orbit of a planet could be calculated centuries in advance. The vibration of a string or the oscillation of a pendulum could be described with precision. There was no obvious reason to suspect that atoms, which were imagined as tiny mechanical systems, should behave any differently. Yet the first cracks appeared when scientists began to study light and heat at very small scales. One of the earliest warnings came from the problem of blackbody radiation. When objects are heated, they emit light, and classical physics attempted to explain this emission by treating atoms as oscillators that could emit and absorb electromagnetic waves of any frequency. The calculations led to a catastrophic prediction. As frequency increased, the emitted energy should grow without limit. This result, later called the ultraviolet catastrophe, directly contradicted experimental observations. Nature clearly did not behave as classical theory demanded. Something was suppressing high-frequency radiation, but classical physics had no mechanism to explain why. At roughly the same time, experiments involving the photoelectric effect created further confusion. When light shines on a metal surface, electrons can be ejected, but only if the light exceeds a certain frequency. Increasing the intensity of low-frequency light does nothing, while even dim high-frequency light can release electrons instantly. According to classical wave theory, energy depended on intensity, not frequency, and electrons should gradually accumulate energy until they escaped. This did not happen. The energy transfer appeared to be all or nothing, hinting that energy itself might come in discrete packets rather than flowing continuously. These puzzles were unsettling, but they became truly alarming when applied to atomic structure. The classical picture of the atom imagined electrons orbiting a positively charged nucleus, much like planets orbit the sun. According to classical electromagnetism, any charged particle undergoing acceleration emits radiation. An orbiting electron is constantly accelerating as it changes direction. Therefore, it should continuously lose energy, spiral inward, and crash into the nucleus in a fraction of a second. If classical physics were correct, atoms would be inherently unstable, and matter as we know it could not exist. Despite this prediction, atoms were obviously stable. Matter did not spontaneously collapse. This contradiction was not a minor technical problem, it was a fundamental failure. Classical physics could not explain why atoms endured, why chemical elements maintained distinct identities, or why matter had structure at all. The stability of the atom stood as silent evidence that the classical framework was incomplete. Another critical failure emerged from the study of atomic spectra. When gases were heated or subjected to electric discharge, they emitted light at very specific wavelengths, producing sharp spectral lines rather than a continuous spectrum. Each element displayed its own unique pattern, like a fingerprint. Classical theory offered no reason for this discreteness. If electrons could orbit with any energy, then they should emit light across a continuous range of frequencies. Instead, nature selected particular frequencies with astonishing precision. Attempts to rescue classical explanations led to increasingly complex and artificial assumptions. Physicists tried modifying electron orbits, introducing damping forces, or proposing hidden mechanisms that might stabilize atoms. None of these efforts succeeded. They either contradicted experimental data or required assumptions that had no physical justification. The deeper scientists looked, the clearer it became that the problem was not a missing detail but a flawed foundation. The issue went beyond technical inconsistencies. It struck at the philosophical core of classical physics. Classical theories were deterministic. If the initial conditions of a system were known exactly, its future could be predicted exactly. This world, you assumed that nature operated like a perfectly constructed machine. Atomic phenomena, however, refused to conform. Measurements revealed abrupt changes, thresholds, and discrete outcomes that could not be smoothed out by better instruments or more careful experiments. Even the concept of measurement itself began to show strain. Classical physics assumed that observation could, in principle, be made without disturbing the system. In atomic experiments, however, the act of measurement often changed the behavior of the system being observed. Light used to probe atoms altered their energy states. Electrons deflected measuring devices. This suggested that classical notions of objectivity and separability might not apply at the smallest scales. The growing list of failures forced physicists to confront an uncomfortable truth. The success of classical physics in the macroscopic world did not guarantee its validity everywhere. Nature appeared to operate under different rules when examined closely enough. The smooth curves of classical equations gave way to step-like behaviors. Continuous energy distributions gave way to discrete values. Predictability gave way to statistical descriptions. What made this transition particularly difficult was that classical physics was not wrong in the everyday sense. It worked exceptionally well within its domain. Bridges did not collapse because Newton's laws were inaccurate, and electrical circuits functioned precisely because Maxwell's equations held true. The failure lay not in incorrect predictions at large scales, but in the assumption that the same principles must apply unchanged at all scales. The atomic world exposed the limits of that assumption. This realization marked a profound shift in scientific thinking. It suggested that theories are not absolute descriptions of reality, but models that apply within certain boundaries. When those boundaries are crossed, and nervous system recovery. The failure of classical physics to explain atomic behavior was not a defeat but an invitation, pointing toward a deeper and more subtle layer of physical law. Out of this crisis emerged the first hints of quantization. Max Planck, attempting to solve the blackbody radiation problem, proposed that energy could be emitted or absorbed only in discrete units. At first, even Planck regarded this as a mathematical trick rather than a statement about reality. Yet the idea refused to remain confined to equations. It reappeared in explanations of the photoelectric effect, atomic spectra, and heat capacity anomalies. Again and again, nature seemed to insist on discreteness. By the time Niels Bohr began to think seriously about atomic structure, it was clear that classical physics alone could not succeed. The atom demanded a new logic, one that accepted limits on what could be known and allowed discontinuous change. Bohr's work did not arise in a vacuum. It was a response to decades of mounting evidence that the classical world view, though powerful, was incomplete. The failure of classical physics to explain atomic behavior was therefore not a single mistake, but a pattern of breakdowns. Stability could not be justified, spectra could not be explained, radiation laws collapsed under their own predictions, and experimental results defied deterministic expectations. Together, these failures revealed that the microscopic world was governed by principles fundamentally different from those governing everyday experience. This moment in history represents one of the most important turning points in science. It taught physicists humility, reminding them that even the most successful theories have limits. It also opened the door to a revolutionary way of thinking, where energy comes in packets, where change happens in jumps, and where probability replaces certainty. The classical framework had reached the edge of its usefulness, and beyond that edge lay the quantum world, waiting to be understood. When Niels Bohr turned his attention to the atom, physics was in a state of intellectual tension. The failures of classical theory had made it clear that something essential was missing, yet no one knew exactly what form a new explanation should take. Bohr approached the problem with a willingness to abandon assumptions that had long been considered untouchable. Instead of forcing atoms to obey classical rules, he asked what rules atoms themselves seemed to follow, as revealed by experiment. From this approach emerged one of the most radical ideas in the history of science, the notion that energy levels inside an atom are quantized. Bohr began with a simple but daring postulate. Electrons, he proposed, can exist only in certain allowed orbits around the nucleus. These orbits are not chosen arbitrarily. They correspond to specific energy values. While an electron remains in one of these allowed states, it does not emit energy, no matter how violently classical physics might expect it to radiate. This idea directly contradicted Maxwell's electrodynamics, yet it immediately solved the problem of atomic stability. If electrons were forbidden from occupying most possible orbits, then the catastrophic collapse predicted by classical theory simply could not occur. The restriction of electrons to specific energy levels introduced a new way of thinking about motion and energy. In classical mechanics, energy is a continuous variable. A particle can possess any value within a range, and small changes in conditions produce small changes in energy. Bohr's atom, by contrast, permitted only discrete values. An electron could occupy one energy state or another, but nothing in between. The atom, in this sense, behaved less like a miniature solar system and more like a musical instrument, capable of producing only certain notes. To give this idea mathematical form, Bohr combined classical concepts with emerging quantum ideas. He adopted Planck's constant, originally introduced to explain blackbody radiation, and applied it to the motion of electrons. Bohr proposed that the angular momentum of an electron in orbit must be an integer multiple of a fundamental unit determined by Planck's constant. This quantization condition had no classical justification. It was imposed as a new rule of nature. Yet from this single assumption flowed remarkable results. Using his quantization rule, Bohr calculated the allowed radii and energies of electron orbits in the hydrogen atom. The results matched experimental observations with striking accuracy. The energies of these orbits corresponded exactly to the spectral lines that had puzzled scientists for decades. Each observed line could be explained as the result of an electron transitioning between two allowed energy levels. The color of the emitted light was determined by the energy difference between the initial and final states, in precise agreement with measurements. This success gave Bohr's model immediate credibility. For the first time, atomic spectra were not just catalogued but understood. The mysterious regularities observed by spectroscopists were revealed as direct expressions of the atom's internal structure. What had once seemed like arbitrary patterns were now seen as the fingerprints of quantized energy levels. The atom, long invisible and abstract, gained a concrete and calculable form. Equally important was what Bohr's model said about the nature of physical explanation. It showed that predictive power could be achieved even when underlying mechanisms were not fully understood in classical terms. Bohr did not explain why angular momentum should be quantized. He simply asserted that it was, because nature demanded it. This pragmatic approach marked a departure from the classical ideal of deriving all behavior from first principles. In the quantum domain, empirical success became a guiding criterion. The concept of quantized energy levels also reshaped the understanding of radiation. In Bohr's picture, light is not emitted continuously as an electron spirals inward. Instead, radiation occurs only during transitions between energy states. When an electron jumps from a higher level to a lower one, a photon is emitted, carrying away a discrete amount of energy. Conversely, when an atom absorbs light, an electron jumps upward to a higher level, but only if the incoming photon has exactly the right energy. This explained the sharp absorption and emission lines observed in experiments. The radical nature of these ideas cannot be overstated. Bohr's model required physicists to accept that classical laws did not apply universally. It also implied that certain questions, such as the precise path an electron takes during a transition, might be meaningless. The model described allowed states and observable outcomes, but remained silent on the details of how transitions occurred. This silence was not a flaw, but a reflection of the limits imposed by nature itself. Despite its successes, Bohr's theory was not a complete description of all atoms. It worked best for hydrogen and hydrogen, like systems with a single electron. For more complex atoms, the calculations became less accurate, and additional assumptions were needed. Nevertheless, the core idea of quantized energy levels remained intact and continued to guide further developments. The model served as a bridge between classical physics and the fully developed quantum mechanics that would emerge in the following decades. Bohr's work also had deep philosophical implications. It suggested that physical reality at the atomic level could not be fully visualized using everyday concepts. Orbits, in Bohr's model, were not literal paths traced by electrons in space, but symbolic representations of energy states. This distinction hinted at a future where wave functions and probability amplitudes would replace trajectories and forces as the fundamental descriptors of nature. The introduction of quantized energy levels forced a re-examination of causality and determinism. In classical physics, knowing the present state of a system allows its future to be predicted with certainty. In Bohr's atom, one could calculate the allowed energies and the probabilities of transitions, but not the exact timing of individual events. This shift from certainty to probability marked a profound change in the scientific world. Perhaps most significantly, Bohr's idea demonstrated that radical simplicity could coexist with deep explanatory power. With a small number of bold assumptions, he resolved problems that had resisted solution for years. His model did not merely patch existing theory, it redefined the conceptual framework of physics. Energy, once thought to flow smoothly, was revealed to be quantized. Stability, once mysterious, became a natural consequence of allowed states. Spectral lines, once puzzling, became inevitable. The legacy of Bohr's quantized energy levels extends far beyond atomic physics. The same principle underlies the behavior of electrons in solids, the structure of molecules, and the operation of countless technologies. From lasers and transistors to magnetic resonance imaging, modern devices depend on controlled transitions between quantized states. What began as a solution to an abstract theoretical problem became a cornerstone of technological civilization. In embracing quantization, Bohr helped physicists accept a new vision of nature, one in which discontinuity is fundamental and limits are built into the fabric of reality. His work taught scientists to listen carefully to experiments, even when they contradicted cherished theories. It showed that understanding the universe sometimes requires letting go of familiar ideas and adopting concepts that, at first, seem deeply counterintuitive. Through the notion of quantized energy levels, Bohr did more than solve the atom. He opened the door to the quantum world. The phrase quantum leap has entered everyday language as a metaphor for a dramatic, transformative change, yet its scientific meaning is far more subtle and, in some ways, more radical. In the context of atomic physics, a quantum leap refers to the sudden transition of an electron from one allowed energy state to another. This idea, introduced through Niels Bohr's atomic model, challenged not only classical physics, but also deeply ingrained intuitions about how change occurs in nature. To understand what quantum leaps truly mean, it is necessary to strip away the metaphor and examine the concept as it emerged from experimental evidence and theoretical necessity. In classical physics, motion and change are continuous. A particle moving from one position to another must pass through all intermediate points. An object changing speed does so gradually, accelerating or decelerating over time. This continuity was assumed to be a universal feature of nature. Bohr's quantum leaps violated this assumption at its core. According to his model, an electron bound to an atom occupies a discrete energy level. When it absorbs or emits energy, it does not slide smoothly from one level to another. Instead, it appears in the new state without ever existing in between. The transition is abrupt, and classical concepts such as trajectory or path lose their meaning. This abruptness was not a speculative invention, but a direct response to experimental facts. Atomic spectra revealed that atoms emit and absorb light at sharply defined frequencies. Each frequency corresponds to a specific energy difference between two states. If electrons changed energy continuously, one would expect a continuous spectrum of radiation. The observed discreteness demanded an explanation, and quantum leaps provided it. The electron's energy changes in precise steps, and each step is associated with a photon whose energy matches the difference between the initial and final states. A crucial aspect of quantum leaps is that they do not describe motion through space in the ordinary sense. The electron does not travel along a visible path from one orbit to another. Instead, the leap is a change in the electron's state, characterized by its energy and other quantum properties. This distinction is often misunderstood, leading to the mistaken image of electrons jumping like tiny particles between circular tracks. In reality, the concept of a jump reflects a change in the mathematical description of the system, not a physical leap through space. The absence of a defined intermediate state raised profound questions. If an electron is not in one energy level and not yet in another, where is it during the transition? Classical physics demanded an answer, but quantum theory refused to provide one. The transition itself became an event that could not be described using classical language. This marked a turning point in physics, where the demand for continuous, visualizable processes was replaced by a focus on observable outcomes and measurable quantities. Quantum leaps also introduced an element of unpredictability. While the allowed energy levels of an atom can be calculated precisely, the exact moment when an electron will make a transition cannot be predicted with certainty. One can determine probabilities, not certainties. An excited atom may emit a photon quickly or after a delay, and there is no hidden clock governing the timing. This randomness is not due to experimental ignorance, but appears to be an intrinsic feature of nature. The leap occurs without a deterministic cause that can be tracked in classical terms. This probabilistic aspect further separated quantum physics from classical intuition. In classical systems, randomness often signals incomplete information. If all variables were known, outcomes could be predicted exactly. Quantum leaps suggested a different kind of randomness, one that persists even when all measurable parameters are specified. This challenged the long-held belief that the universe operates like a perfectly predictable machine. The energy carried by light during a quantum leap is another key feature. When an electron drops to a lower energy level, it emits a photon whose energy is precisely defined. This energy is not spread out or divisible. It is a single quantum. Conversely, an electron can absorb a photon only if its energy matches the gap between two allowed states. Photons with slightly more or less energy simply pass by or interact differently. This selectivity explains why atoms are transparent to some frequencies of light and opaque to others. The concept of quantum leaps also clarified the meaning of atomic excitation. When an atom absorbs energy, it does not store that energy in a continuous way. Instead, the electron occupies a higher energy state. The atom remains in this excited state until a leap occurs, releasing the excess energy. During this time, the atom has well-defined properties corresponding to the excited state, not a mixture of intermediate energies. This behavior defies classical expectations, but is consistently confirmed by experiments. As quantum theory developed beyond Bohr's model, escape is possible. Wave mechanics replaced orbits with wave functions, and energy levels emerged as solutions to fundamental equations. In this framework, a quantum leap corresponds to a change in the wave function of the system. The suddenness of the transition reflects the discrete nature of the allowed solutions. While the mathematical description became more sophisticated, the essential idea of discontinuous change remained. Importantly, quantum leaps are not violent or large-scale events. Despite the dramatic language often associated with them, they involve extremely small changes in energy and occur at scales far removed from everyday experience. The metaphorical use of a quantum leap to describe major breakthroughs is therefore ironic, as the original meaning refers to the smallest possible change permitted by nature. This highlights the disconnect between common language and scientific terminology. The refusal of quantum leaps to conform to classical pictures had lasting philosophical consequences. It forced physicists to reconsider what it means to explain a phenomenon. Instead of describing mechanisms in terms of forces and trajectories, quantum physics describes relationships between states and probabilities of transitions. Explanation became less about visual models and more about predictive frameworks. This shift was unsettling, but ultimately fruitful, leading to a deeper and more accurate understanding of the atomic world. Quantum leaps also underscored the role of measurement in physics. The emission or absorption of a photon is an observable event, and it is only through such events that transitions are detected. The leap itself is inferred from the change in the system's state before and after the event. This emphasis on observable quantities aligned with a growing recognition that some aspects of microscopic reality might be inaccessible to direct observation. The concept continues to influence modern physics. In quantum optics, controlled quantum leaps are used to manipulate individual atoms and photons. In quantum computing, transitions between discrete energy states form the basis of information processing. In chemistry, electron transitions determine reaction pathways and molecular properties. The idea that systems evolve through discrete changes rather than continuous motion remains central across these fields. What quantum leaps truly mean, then, is not simply that electrons jump between orbits, but that nature itself operates in a fundamentally discrete way at its deepest level. Change does not always flow smoothly. Sometimes it occurs in steps, without intermediate states. This realization shattered the classical illusion of continuity and replaced it with a vision of reality that is both more constrained and more mysterious. By embracing quantum leaps, physicists accepted that some questions may not have classical answers, and that the absence of a continuous narrative does not imply a lack of understanding. Instead, understanding comes from recognizing the patterns and rules that govern allowed states and transitions. The quantum leap stands as a symbol of this new way of thinking, a reminder that the universe often defies intuition and demands new forms of explanation. The impact of Niels Bohr's ideas did not end with the explanation of atomic spectra or the stabilization of the atom. Their true power became evident over time, as the concept of quantized energy levels and quantum transitions reshaped both theoretical physics and the technological world. What began as an attempt to solve a specific problem evolved into a framework that transformed how scientists understand matter, energy, and information. The influence of Bohr's model extends across disciplines, quietly underpinning much of modern science and everyday technology. In the years following Bohr's proposal, physicists expanded and refined the quantum picture of the atom. While Bohr's original model was limited in scope, its central insight survived every refinement. The idea that electrons occupy discrete states became a cornerstone of quantum mechanics. Schrödinger's wave equation replaced classical orbits with wave functions, yet the resulting energy levels mirrored Bohr's predictions in the appropriate cases. Heisenberg's matrix mechanics, developed independently, arrived at the same conclusions through a different mathematical route. These parallel developments confirmed that quantization was not an artifact of a particular model, but a fundamental feature of nature. This theoretical consolidation had immediate consequences for chemistry. Chemical bonding, long described empirically, found a deeper explanation in terms of electron energy levels and quantum states. The periodic table, once an organized list of elements, became a map of electron configurations governed by quantum rules. The stability of noble gases, the reactivity of alkali metals, and the diversity of chemical behavior all emerged naturally from the arrangement of electrons in quantized shells. Bohr's insights thus bridged physics and chemistry, revealing them as expressions of the same underlying principles. In solid-state physics, quantization proved even more transformative. When atoms come together to form solids, their discrete energy levels broaden into bands. The presence or absence of electrons in these bands determines whether a material behaves as a conductor, an insulator, or a semiconductor. This understanding made it possible to engineer materials with specific electrical properties. The transistor, the fundamental building block of modern electronics, relies on controlled electron transitions between energy bands. Without the quantum framework initiated by Bohr, such devices would be inconceivable. The development of lasers offers a particularly clear example of quantum ideas translated into technology. A laser operates by stimulating electrons to make synchronized quantum transitions, emitting photons that are identical in energy and phase. This process, known as stimulated emission, depends entirely on the existence of discrete energy levels. Lasers have become ubiquitous, used in medicine, communications, manufacturing, and entertainment. Each laser beam is a practical demonstration of Bohr's legacy, a stream of light produced by countless coordinated quantum leaps. Quantum ideas also revolutionized the understanding of light itself. The interaction between atoms and photons, once mysterious, became a central topic of quantum electrodynamics. Precision experiments confirmed predictions to extraordinary accuracy, making it one of the most successful theories in science. Atomic clocks, which measure time by monitoring transitions between specific energy states, now define the standard for timekeeping. These clocks are so precise that they can detect tiny differences in gravitational potential, linking quantum physics with general relativity in practical applications. Beyond technology, Bohr's work reshaped the philosophy of science. His emphasis on the limits of classical concepts led to the principle of complementarity, which states that certain properties of quantum systems cannot be simultaneously described using classical terms. For example, particles can exhibit both wave-like and particle-like behavior, but not at the same time in the same experimental context. This principle challenged the notion that a single, unified picture could capture all aspects of reality. Instead, it suggested that different experimental arrangements reveal different facets of the same underlying system. The acceptance of probability as a fundamental element of physical law marked another profound shift. In classical physics, probabilities reflect ignorance. In quantum physics, they are intrinsic. This change required scientists to rethink the meaning of explanation and prediction. Bohr argued that the goal of physics is not to reveal how nature is, but to describe what can be said about nature based on experimental evidence. This pragmatic stance influenced generations of physicists and shaped debates about the interpretation of quantum mechanics. The legacy of Bohr's ideas continues to unfold in contemporary research. Quantum information science, which seeks to exploit quantum states for computation and communication, builds directly on the concept of discrete energy levels and controlled transitions. Quantum bits, or qubits, rely on superpositions of states and transitions between them. While these ideas go beyond Bohr's original model, they remain rooted in the quantized structure he helped establish. The pursuit of quantum computers is, in many ways, an extension of the same principles that once explained the hydrogen spectrum. In astrophysics, quantum transitions play a crucial role in interpreting light from distant stars and galaxies. Spectral lines reveal the composition, temperature, and motion of celestial objects. The same rules that govern electrons in laboratory atoms apply across the universe, allowing physicists to read cosmic information encoded in light. This universality underscores the depth of Bohr's contribution. A theory developed to explain atomic behavior on Earth also illuminates the structure of the cosmos. Educationally, Bohr's model remains a gateway to quantum thinking. Although simplified, it introduces students to the idea that classical intuition must sometimes be set aside. By grappling with the concept of quantized energy levels, learners encounter the first hints of a world where certainty is limited and discrete choices replace continuous variation. This intellectual challenge is not merely technical. It cultivates a broader understanding of how scientific knowledge evolves. The broader cultural impact of quantum ideas is also notable. Terms like quantum and uncertainty have entered popular discourse, often stripped of their precise meanings but retaining a sense of mystery and transformation. While such usage can be misleading, it reflects the profound impression quantum theory has made on the collective imagination. Bohr's willingness to embrace counterintuitive ideas became a symbol of intellectual courage and openness. In evaluating the long-term significance of Bohr's work, it is important to recognize both its limitations and its enduring insights. His original model was incomplete and eventually superseded, yet its core concepts survived every refinement. This pattern illustrates how scientific progress often works. Ideas are not simply discarded, but transformed and absorbed into more comprehensive frameworks. Bohr's contribution lies not in the permanence of his specific equations, but in the conceptual shift he initiated. Ultimately, the redefinition of physics brought about by Bohr's idea of quantized energy levels changed humanity's relationship with the natural world. It revealed that the universe is governed by rules that defy everyday intuition yet exhibit a deeper order. By accepting discreteness, probability, and limits to classical description, physicists gained access to a richer and more powerful understanding of reality. The technologies that shape modern life, from computers to communication networks, are silent witnesses to this transformation. The story of Bohr's legacy is therefore not just a chapter in the history of physics, but a continuing narrative. Each new application, each experimental confirmation, and each theoretical advance echoes the original insight that energy comes in steps and change can be sudden. Through this idea, Bohr helped humanity take a quantum leap in understanding, one whose effects continue to unfold across science, technology, and thought itself.